Alrighty, this particular video looks at the idea of torque. When we look at his role in circular motion, we spent time talking about the idea that centripetal acceleration, the rate of change of direction of my motion, was governed by centripetal force, because all accelerations are produced by a force. However, there is another acceleration involved in circular motion, and that was tangential. And tangential acceleration was involved in the rate of change of speed of the motion. Well, accelerations report things. They report a rate of change. He doesn't cause, however, the change. So who sort of takes centripetal force's job when I'm thinking about tangential acceleration? That's torque. Torque is defined as the ability of a force to produce or alter rotation. So I can start something rotating. I can stop it. I can make it speed up or slow down. All of that is torque's job. Centripetal force just keeps him going in a circle. Centripetal force opposes the inertia and makes him, or at least the direction part of that inertia, and makes him go in a circle instead of a straight line. The speed part of the inertia, that's what torque is taking care of. So torque by himself is not a force. He's what we call a force analog. He does the job, but he's a little bit more complicated than just a single force by himself. If I want to calculate torque, his formula in full looks something like this. FD sine theta. Now the FD part on its own reminds us very much of work. And torque and work are oftentimes very similar in what they're doing in a system. However, a big difference is in the definition of this distance. In work, that distance could just be how far was a box pushed across a floor. However, when we're dealing with torque, it has a very specific meaning. Let's say I have a seesaw, and I've got a kid sitting over here, and I want to know how much torque is he applying to this seesaw. Well, the force in this case would be his weight. Oftentimes force is weight. So when they're giving you masses of things in equations for torque or work or anything like that, think about converting those over to force immediately. Mass to force, multiply it by gravity. And the d value is how far is he from the axis of rotation. And another way of saying axis of rotation is pivot point. So however far the kid is from that center part of the seesaw times his weight would be on my way to calculating torque. If another kid was sitting closer, even if he had the same weight, because his distance is smaller, he would produce less torque. So the size of your force influences torque, but so does where you apply that force. Now I know I'm not paying attention to this piece right here. I'll get to that in a minute, but let's just hang on to these first two variables and make sure we understand what they're doing. If I right now just kind of, and I'll go ahead and erase him, concentrate on these two. Why does this poor kid produce less torque? Shorter lever arm. He has less ability to rotate my seesaw. They have the same weight, but a shorter lever arm means less torque. The kid with the longer lever arm has more torque. Which is why when we're dealing with something like a wrench, and oh, you know, if I try and draw this wrench, it's going to be a horrifying thing, but I'll do it. Just don't laugh at me. There, it's kind of like a wrench. If I can't get this particular nut to turn, what do? Go get a longer wrench. Find someone whose handle is maybe even longer in comparison to that one. Because that longer handled wrench, there's my axis of rotation, center of your bolt, your nut, to wherever I put my hand. That's lever arm. If I make that distance bigger, whatever force I can apply, I get a lot more torque out of it. So when I'm working with something like a wrench, that's why they have long handles. Crowbars, that's why they have long handles. There's my hand. Right there is your axis of rotation. That's where effectively he pivots. The longer this is, the more torque I have. So when looking at the idea of torque, changing lever arm will give you more or less torque. Changing the size of the force gives you more or less torque. But now, what about that pesky sine theta piece? Well, consider a bar. I'm going to hinge this particular bar. This might be something like, a bar that would have a sine attached to it. And I'm going to apply a force to that bar. Well, this force, of course, is at an angle. And everything that's at an angle can be broken up into two pieces, an X and a Y. One of my pieces runs right here along the door, and the other piece runs upwards. Now just physically think about what would happen if you grabbed onto each of those components of the force. If I grabbed onto this component, the X, and I pulled him in this direction, which is how he's pointed, all I'm going to do is pull the bar straight across the page. That's all I'm going to do. He's sure as heck not going to rotate. However, if I pull on the Y force, in this case pulling up, my door is going to rotate. He's going to start to move upwards and then keep pulling in that direction, always at 90 degrees to the door. He's going to keep going round and round. So when I am, let's say, here, with my door, that force is still, that component is still like that. It's still pulling him over. When the door is like this, that component of the force is like that, still pulling him over. The other component, this guy, he's right along the plane of the door here. He's right along the plane of the door there. No torque, no rotation. So the reason that sine theta part is in there is when I have a force that acts at an angle, the only piece that contributes to torque is the piece that's at right angles to what's rotating. So this component of the force produced torque. And for this example, I would find him using the sine function. He's the side of the triangle opposite the angle. But as I had said, watch in problems when instead the angle you're given is someone like this. In that case, if I use the sine function, I would get that component of my force. That's not going to produce rotation. That's just going to drag him to the left. I actually need this side of my triangle. And before you say, oh wait, that's at the base somehow, and you're looking towards the tip, remember, it's the same as that one. That's the one I need. And so for this one, I would use the cosine function, not the sine function. So, let's take a look at what a problem would look like from this stage, at this stage of the game. Let's say I have a nice bar. Let me draw him down a little bit farther, I guess. I'll draw him over here. My bar pivots right there. That's where the hinges are, or something along those lines. One force is acting. He's 15 newtons. And I have an angle that I'm given of 30 degrees. I have another force, and I'm given this angle. Oop, let me make him a little shallower. He looks a little large for the angle I actually chose. That angle is 15 degrees, and the size of the force is 25 newtons. Third force is down here. His angle, 35 degrees. His size is 40 newtons. And I want to solve for really two things. One, what is the torque produced by each of the forces? So the torque by the 25 newton, the torque by the 40, and the torque by the 15. And then I want to sum all those guys up and get the net torque. Well, in order to get torque, I need one more piece of information, and that's lever arm. So from this particular force right here to the axis of rotation, let's say it's 2 meters. That distance to here, 2 meters. this distance to here, that distance is 0.8 meters. This distance to here. This particular force acts directly at the axis of rotation. When I go to do my calculation, doesn't even matter what the angle is, doesn't even matter what the force is. I have got a distance between where the force is applied and where it rotates of 0. When a force acts directly on the axis of rotation, torque is 0. So any time you see that nice force and he is being applied directly to the hinges of the door, directly to the axle of a bike wheel, whatever it might be, this guy, get rid of him. No torque. Zippo. Squat diddly. And so over here, boop, 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 boop. My 15 Newton force, torque, 0 Newton meter. And Newton times meter is the appropriate unit for torque. So now we gotta look at the other two. My 25 Newton force acts 0.8 meters from the axis of rotation, so that's pretty quick and clear. 25 times 0.8 times. He does act at an angle, and I have to think. Which component of the force? This one that pulls this way, or the one that pulls that way, actually acts at right angles to the door. That's the winner. That's the adjacent side to the angle, cosine of function. Cosine of 15. Now in truth I'm not done, because torque does have a sign, positive or negative. Torque is positive when the rotation is counterclockwise. Torque is negative when it's clockwise. So think about myself pulling with this guy upward. That would swing the door up and over like that. That's counterclockwise. That torque is going to be positive. And it turns out to be 19.3 Newton meters. So now we attack the other one. I have 40 newtons acting 2 meters away from the axis of rotation. I have an angle I have to deal with, 35 degrees. So I break my force into components. There's the X and there's the Y. Which side acts perpendicular to the door? That side does. And I do find him with the sine function. So sine of 35 is the last piece to my formula. But I have to ask about direction. Which way does this guy rotate? Well, if I grabbed on to that and pulled down, my door would swing like that. Again, it's counterclockwise. So this particular torque, which calculates to 45.9 Newton meters, is also positive. Then it's simply a matter of summing them all up, and I wind up getting a net torque. I've run out of room. I have no idea where to write this. I'll erase part of my problem. The magic eraser. There we go. Net torque, a positive 65.2 Newton meter. And if we're asked for the direction of rotation, it's counterclockwise. So when I'm dealing with a situation, it could be like the problem in your book where it was like a ball, and a force is acting there, and a force is acting there, and they tell you how far they are from the center. Well, both of those act at right angles. What's his torque? What's his? I don't need the sine theta because they're acting already at right angles. This guy would rotate him counterclockwise, positive. He would rotate him clockwise, negative. Add the two together, that's your net torque, and the sign determines clockwise or counterclockwise rotation. But when I have something like a door, or a sign, or a bar, or who knows what it is, where's the axis of rotation? The distance between each force is your lever arm. I should say the distance between each force to the axis of rotation is lever arm. Some forces might be at right angles. So that guy's just FD, done. Some I would have to look. Which part of the force acts at right angles to the door or the bar? That's the piece of the force I use in my calculation of torque. Keeping my eye on which angle I'm given. So this particular force with that angle, I had to use the cosine function because I needed that part of the triangle. If I'm given this angle here, I was able to use the sine function. And of course, don't forget, anyone applied directly to the axis of rotation himself, big goose egg for torque. Alrighty, so with torque, make sure you can discuss in general what happens if I change the size of the force, what happens if I change lever arm, make him longer or shorter, what happens if I alter the angle, be able to then go right into calculation, thinking about my angle before I just blindly use sine, thinking about the sign, is it positive or negative for my torque, is it going to be counterclockwise or clockwise, and be able to calculate net torque for my system.